Hi, I'm Gary, and I want to show you how I use Cloudy. In this video, I want to talk about how we set the incident radiation field coming into a cloud. This slide summarizes the cloud parameters, and the first thing we have to do is specify an energy source. It could be mechanical energy, like a shock or something, but in many cases, it's the radiation field coming in. If the cloud is close to a source of ionizing radiation, mechanical energy in the accretion disk is converted into light, which then energizes cloud somewhere else. So it's photonization equilibrium. And to get started, we need to specify that radiation field. That's what we're going to talk about in this video, the shape of the radiation field. There are other cloud parameters, which we went over once before when we set up the M16 homework problem. So you got to specify a cloud density, a thickness, its composition, uh, and a couple of other details. And what you get back are thousands of observables. So it's a nice problem. So we're going to talk about today is the incident radiation field. It's specified in two parts in Cloudy. One is the shape of the radiation field. The second is its brightness. We have to be able to figure out the number of photons per square centimeter per second, because at the microphysical level, that's what is multiplied by the cross section in square centimeters to figure out a rate in seconds to the minus one. So it's got to be able to figure out a flux of photons per unit volume, per unit area, per square centimeter. So we can talk about that as the shape command. The intensity is separate. As an example, a quasar may have a particular SED, a shape. If you're 1 parsec away from the quasar, there's a very strong flux of radiation hitting. If you're a megaparsec away, then the flux is very faint. The SED shape doesn't change, but the brightness does. We separate them quite independently. So there's several ways the three main ways of specifying an SED. And I'm going to show this in this input script, which will be running. So this is a bare minimum cloudy input script that's designed to be fairly fast. So we're going to look at a blackbody, brems shape. So these are fundamental shapes. They come from equations. These are the table SED is a very widely used way to get a shape in. You build a table that gives a energy and a flux. Can be in several different units. So just an XY table. Drop it in this one directory, and then you can access it with table SED. We also have the results of large grids of stellar atmospheres that have been contributed to the code over some time. And it's possible to do, if the author provided such a grid, uh, three-dimensional interpolation over density, over temperature, log G, and surface gravity. Uh, the rest of the model is pretty standard. We just make cloudy function that if a cloudy checks that it has enough information for a model, it won't try if it can't. So there's luminosity, hydrogen density, and then inner radius. So we specify the total luminosity of the star, that's ergs per second, and we're a bit under a parsec away from it. So then it can figure out the number of the luminosity per square centimeter per second. And then we're going to save the continuum in this file, which we're going to be plotting. These are some speed ups. So this turns off everything except hydrogen. That's going to make it really fast. That's the bare minimum. This turns off the temperature solver and it stops in zone one. Okay, so let's make sure this is written. I'm going to go over to another tab and run this demo. Okay, it's done. Let's go over to views. I've set up this plot. I'll say data reload. This is our black body. On this plot, the infrared, this is in microns, an SI unit of wavelength. This is the near infrared, and this is now the XUV, EUV. The blue line for a photoionization calculation is an important point. This is the energy it takes to ionize hydrogen. And so all the radiation field to the left of this line can ionize hydrogen and create ionized nebulae. So we should be paying attention to this. So this is just a simple black body. Let's do something else. Another fundamental one is free emission or brems emission. So let's go compute that. Have a look. Okay, it's done. Data reload, and we have brems emission. So this might be the emission from intercluster medium in a galaxy cluster. Not quite a black body, but black body-ish. It's got a two high and low frequency extremes. So let's go on and look at something else. Table SED are the family of commands that allow you to specify the radiation field as an XY table. So it might be something you generate from another code. It could be from something from Excel or something like that. And so on its own, if you say table SED indice 5548, what it's going to do is look in a directory in data SED, and it's going to look for a file that has that name. This particular file was generated by Mariam Dehanian and is a representation of a C4 galaxy that was very well studied in the Storm HST campaign. So it's available, and two forms of the SED are there. So what this command does, you just say table SED, and it uses the a file as a source of as the source of an SED shape. So let's write this and have a look at the quasar. Okay, data reload. So it's a much harder radiation field extending out even to the hard X-ray. Let's go back. You can you can get a list of all the SED files that are in data SED in two ways. You can just CD down into data SED and do an LS, or you can in the command deck, you can include this command that says table stars available. That'll generate a report of which SED files are there. If you generate your own SED files, they're very straightforward. You might consider contributing it back to the Cloudy project, and we could include it in this distribution. It does have to have provenance. It has to have a publication that can trace back where it is. The next way we have this is the result of an LS in the data SED directory, and you get a similar report with a bit more detail if you do table SED available. The last way is actually the more powerful if it happens to suit your purpose. There's large grids of stellar atmospheres that have been produced, and Cloudy can interpolate on these grids. In some cases, they may be three-dimensional grids where you have a stellar temperature, surface gravity, and metallicity, and you can do a three-dimensional interpolation on these stellar atmospheres. I'll show you one in just a second. So you can generate a report of which ones we have with this table star available. So let's go back to our model and let's do a T-Lusty was a beautiful program by Ivan Huvenet, and he has done a lot of work with it, and there are large grids available out there. So I shall run it. Okay, let's have a look. Data reload. So now you have a very relativistic immersion spectrum SED from a star. You can see a Lyman jump here. This is the Lyman edge. And you can see a lot of absorption lines in the stellar atmosphere. So this is the ionizing radiation is quite different from a black body. This is one order of magnitude. So that's a summary of those table SED commands and other ways of setting the SED. They're all described in chapter 6 of Hazy. So it's worth passing your eyes over the table of contents or going deeper into it. There's a lot of options present. So see you next time. Thank you.